So let us continue with the design of the plate girder. So what exactly we are doing, you observe here. You can see this one. These are three plates are there. Plate girder is nothing but a very large beam. Three plates are there. We have to design these three plates which will act as a big beam or a girder to take care of bending moment and shear forces. Now, as I explained yesterday, either it can be bolted or it can be welded. So we are going to study only the welded plate girders. In that one, 3-4 types are there. Presently, we are going to deal with the design of plate girder without stiffeners and with stiffeners. So you can see the steps here. Now I'll explain the problem here. Now what exactly we are doing, observe here. What is your job here? What exactly we are trying to do in this case? Because span and loading will be given only with respect to span and loading only we are supposed to completely design the plate girder. Now observe what I will be doing here is, now observe this one here. What exactly is done here? This is one plate. You can say this is one more plate is here. These two are flanges, and as you can see, this is one web is there. So in the design means what we are going to do is we have to decide the dimensions of these flanges, dimensions of both the flanges, and check them whether they are able to, whether they are capable of resisting the bending moment or not. Second is, uh, once you, this one, second important thing is web design. Web is meant for resisting the shear. You have to finalize the dimensions D and D and thickness. You have to finalize the dimensions of this web here. So web is mainly meant for resisting the shear. Flanges are meant for resisting the bending moment. So how to design, how to decide the thickness, how to decide these dimensions of the both the flanges, dimensions of both the, dimension of this web, and how to interconnect them using welds. We need to interconnect these members using welds. Where it is done, you can see here, where it is done is, and how the welding is done. So weld is applied here, this side also. I'll show you the exact figure later on. Here the weld is applied. So these are all along the length of the girder. I have to apply the welds and connect them. These are intermittent welds due to cost factor as well as strength. Even if the welds are intermittently connected, which we can see in the longitudinal section, not here, but you will come to know that these are all intermittent welds. Now you observe here. So let us see here what is done. I'll show you now. So ultimately, I have to find out all these dimensions and check the flanges whether they are sufficiently strong enough to resist the bending moment. Also check this particular web whether it is sufficiently strong enough to resist the shear. Once that is done, we can say the design is safe. And stiffeners and all stiffeners and bearing. One more important thing in case of steel structure, as you may be knowing this one, I'll show you, observe here. What is important in case of steel structures apart from this? Apart from this is, observe this. So let us say this is the support. Elevation is elevation. Let us say this is a support here. And there will be one concrete block always. Either it is a column, if it is made of brick masonry or something like that, there will be a concrete block will be there at the top, which is meant for dispersion of load. Now observe here. There will be a concrete block. This is a concrete block here, this much. Now, I want to place this I section. It looks like I section. I want to place this plate girder on the supports on either side. On either side. What is not usually done in RCC, but here it has to be done. Here is just observe. What I should do here is there is one more design part. It is apart from designing all this, you have to design the bearing, stiff bearing, and how much should be, how much it should come inside the beam. How much it should project on this particular, you see, bearings. It is called as bearing. I will show you that one. Observe this. So I'll draw this longitudinal section of this plate girder. Let us say it is something like this. This is your plate girder longitudinal section. Important is how much is this? How much should be this stiff bearing? We call it a stiff bearing. Now, what is stiff bearing? You observe. That is one important calculation will be there. Now, stiff bearing means this much. How much is overlapping? So this is what is called as B1. Now B1 has to be assumed, and after assuming B1, use the formula given in the code book and check whether this B1 whatever we assumed is sufficient or not, or whether I should increase it or reduce it also if it is more. Now observe this one here. What is bearing means what? This portion, as I told you, this portion we call it as B1. We have to assume this B1 as usually 100 mm. Usually this is assumed as 100 mm unless it is given in the problem. Assume B1 as 100 and try to check whether 100 mm is sufficient or not. Usually practically what they do, they don't go for they don't go for this one, they completely support it. If there is a provision is there at the site, they will bring this one up to the end of this other end of the this one, even though it is more, but normally it is done in real life. But in the design part, we have to calculate this distance, or you have to assume some value and check whether that value is sufficient or not. That calculation also I will explain. Purposely, I have not given any code book references here. You just check it later on. All formula is available. Once you go through this solution and check where those open the codebook pages and check, afterwards I'll give you that. First you try on your own. Solution I'm giving here, just observe. Now let us start the design here. As I told you in the previous class here, step number 1 is bending moment shear force calculations are there. It is, you have to calculate this WU, you have to calculate this one, and span is there. Simply WU into L square by 8 is bending moment, and WL by 2. WL by 2 is shear force. So that has to be calculated first. So design a welded plate girder of span 24 meter, carry a superimposed load or service load, it is 35 kN. Avoid use of bearing and intermediate stiffeners. Bearing stiffeners and that problem I'll solve it. Second example will be, I'll be designing this also, these two. First example will be very basic. It is basic to understand how the design is done. Use E250 steel. Now I have drawn this figure. After calculation, I am going to write 58.3 after calculation here. See, so superimposed load is 35 kN meter. Find the factor load. Whatever load is given in the problem, multiply that by 1.5. You have to read it carefully. Read the problem whether it is factored or unfactored. So here it is given as service load, means unfactored. So 1.5 into 35, 52.5. So 52.5 is the factored UTL coming on the girder. What about the dead load of the girder? use this formula WL by, this is there in the code book. Wherever is there, you later you check it. Afterwards, I'll give that WL by 200. Now what I'm doing is, from the factored imposed load, I'm going to find self weight of the girder per meter. Simply WL by 200. W was factored load into L is span is 24 meter given in the problem, divided by 200. It is an empirical formula. 6.3 I got it. Actually, later you should check after a complete design whether the plate girder, after getting all those dimensions, whether is it more or less than this. If it is less than this, it is okay, no problem. Dead load can be checked later. So WL by 200, the formula is used. Total factored load is superimposed plus dead load. Now this is 58.8. This is what is written. Actually, it should be 58.8, I think. That is what should be written here. So this is how load is calculated. Once load is calculated, WL square by 8, WL by 2. Shear end. Now I'll go to the second step. Observe here. So load is calculated. Once the load is calculated, including the dead load of the girder, simply WL square by 8, WL by 2. So 4233.6, 705.6 are the values. Then determine the economical depth of the web plate, D. Observe here, what is that? I'll show you now. What is web plate? What I'm trying to find out here. This one. You can see the diagram. My job is to finalize this height. How much will be this? That is what is there here. That is what I have done here. See, D is equal to cube root of M into K by Fy. Observe here, M into K by Fy. See, if I want to avoid the stiffeners are provided to increase the stiffness of the web. There will be a buckling of the, as you know, the buckling phenomena. There will be a buckling of the web near the point loads. To avoid that one, stiffeners are provided. But here the thickness is sufficient. I'm going to provide sufficiently thick web so that it will not buckle under point load. Under the point load, it will not buckle. For that one, what condition I should use is, as per the code book, this K is if stiffeners are to be avoided. In this problem, I am not designing stiffeners. If I want to avoid the stiffeners, the web should be sufficiently thick. For that one, I will use this condition. D by TW should be less than or equal to 67. What is D? I have shown it here. The ratio between D by TW. This is D, this is TW. So D divided by TW ratio should be equal to or less than 67. First of all, what is D? This is D here, which will be calculated. 1000 is, I have calculated it actually, but right now I'm doing it. So this is D, this is TW. This ratio should be less than or equal to 67. I'll keep 67 only, so that I don't have to design stiffener, so that thickness will be sufficient. TW will be sufficient. Now what I will do? Observe this. K is equal to ratio of D by TW. K means 67 I have kept here. M is 4233.6. See this. 4233.6. That is maximum bending moment. Fy is as usual 250. Cube root of this. Now I got approximately what should be the D value. 1035. I'm not sure. This calculation, I think I have done some 1035.8 or 1049.9. You check it. But what I have done is, whether this or this, I have taken 1000, very close to 1000 it is. Somebody can keep 1050 also, there is no problem. If you say that I will keep 1050, 1049 is there, 1050 I'll keep. But what I have done is, this is, since it is an approximate formula, I have taken it as 1000 mm. Now, see, try D is equal to 1000 mm. Now, what I have done is K is equal to d by tw. Therefore, tw is equal to d by k. Because see, I have fixed 1000. What about the thickness of the web? Tw. So once I know this, tw is equal to d by k, 1000 by 67. Is it clear this one? What I have done here is k is equal to d by tw. K is fixed as 67. D is 1000. Tw can be calculated. So 14.6. Next even number is 16 mm. 14.9. Next even number is 16 mm is selected here. Now, thus web plate selected is 1000 by 16. So the web plate is designed now. Okay, depending upon the span, I need the length. Length depends upon the span, and we have to connect them. In the market, I will not get the 24-meter length, web length directly. I have to just again connect them. That connection is not there. Let us worry about only the basic design part first. So I need a web plate of size 1000 by 16 and length is 24 meters. Length is 20 because span is 24. This is how this plate is designed. What is important here is if you want to avoid the stiffeners, it should be sufficiently thick. 16 mm is sufficiently thick actually. It will avoid the stiffeners. There is no buckling effect under the point load because this condition is satisfied. D by Tw is less than or equal to 67. If this condition is satisfied, no need to provide any stiffeners. So using that condition only, the thickness and depth are finalized. So it is 1000 by 60. So this is the diagram now. You can see this is finalized. So step 3, step 2 is over. In step 2, I have completed web design. Still it is to be checked. It has to clear the checks. That is different. If it fails in the checks, again I have to revise this. Right now, it is 1000 by 16. Before checks, before any checks. Step 3, determine the flange dimensions, area of the flange. Now you look at the flanges. Assuming entire moment is resisted, this word is not clear, but it is resisted. Assuming entire moment is resisted by only flanges. Flanges are meant to resist the bending moment. Web is meant to resist the shear force. Area of the flange is obtained by moment capacity of the flange or flanges equated to factored bending moment. Simple formula it is. That is moment of resistance is equal to bending moment. We are not going to consider any contribution of the web in resisting bending moment. It may contribute, but we are not going to consider that. It is just like in RCC, we say that concrete in tension zone is not considered for any calculations. Concrete in the tension zone is ignored. Similarly, what we are doing here, we are going to ignore the contribution of web in resisting the bending moment. We are going to assume only flanges are resisting the bending moment. So that is why moment capacity of the flange must be equal to factored bending. So let us see that one. Now observe this. Using that condition, I am going to decide the cross-section dimensions of the flanges. What condition is used? You should understand the basics first. Because one can use the STAD or ETABS, but if you don't know the basics, there is no use of that. Just observe this. What is the condition? I'm going to see, my job is to find out the dimensions of the flanges. The condition is this. I'm going to use this condition to arrive at the dimensions of flanges. That is what I'll be doing. Observe here. Now remember, moment carrying capacity of the flanges is equal to factored bending moment. That condition I'm going to use. Just observe this. Moment carrying capacity AF FYD divided by 1.1. Clearly observe this formula here. Just observe this. What we have done here is This is the LHS is the moment carrying capacity of the flanges. This must be equal to the external bending moment. AF, which is to be calculated, area of the flange, 250 is Fy into D is 1000 divided by safety factor, partial safety factor. So this is equated to maximum bending moment. From this, AF is unknown here, 18,628 mm square. Now what we will do is keep the flange in semi-compact category. You have to refer the table. I want to see that the flange must fall in semi-compact category. Okay. All of you type your USN there and division. 82 students are there, 81. You can type your, now observe here. Okay. Now after finding this, after equating moment carrying capacity of the flanges with maximum bending moment, okay, you are getting area of the flange. Once you find area of the flange, from this one I have to finalize the cross section dimensions. To keep the flange in semi compact category, I must see that when I choose B and TF, when I choose B and TF, width of the flange and thickness of the flange, when I finalize these two values, they must satisfy this criteria. Then only the flanges will fall in semi compact category. In that way, you have to finalize. Just observe this. What I'm trying to tell you here is, see, now I know that the area of the flange is this much. Now I have to finalize what is B and what is TF. For that one, I should see that after finalizing B and TF values, it must fall in semi-compact category. It will be in semi-compact category if these conditions are satisfied. B by TF is equal to 13.6. TF is equal to B by 13.6. Epsilon and all, it is 1 because Fy is 250. When Fy is 250, epsilon will be ratio. Square root of 250 by Fy, it will be 1 only. So there is no problem of epsilon there. Now, but try TF is equal to B by 12. Now what I have done here is, now observe these conditions here. TF is equal to B by 13.6 or less than this. Maximum is B by 13.6. But what I am using here as a trial, it is as a trial. Instead of 13.6, I am using TF is equal to B by 12. This condition you have to understand. You should understand what I have done here. Observe this. Actually, TF should be less than or equal to B by 13.6. Now what I have done here is, roughly what I have done, instead of TF is equal to B by 13.6, I am going to try with TF is equal to B by 12. Now I know the relation between TF and B. I know the area AF. I can easily find them separately. Because what is this AF? AF is nothing but B into TF. B into TF is this area of the flange. Okay, area of the flange is B into TF. So I am having an interrelationship between B and TF. B is equal to 12 TF. What I can do here, 12 TF into TF is equal to 18,628. That can be done. Observe here. Because interrelationship between these two dimensions is fixed. See, while fixing a B is equal to 12 times TF, what condition I am using here? I am trying to see that this condition, if I use, it will fall in semi-compact category. The flange will fall in semi-compact category. Okay. Sorry. Then see, I can still use this one. That is B. That is this formula directly. You can simply use 13.6 also. There is nobody will question. But just to round it up as a trial, I am doing this as a trial. Very close to this. I have rounded up this 13.6 as 12. That's all. I'll be in the safer side. AF is equal to B into TF. AF is already calculated here, 18,628. How I got it? Equating moment carrying capacity of the flange with factored bending moment. I got AF. Now I know that AF is area of flange B into TF. Now what I will do? B is equal to 12 TF. I'll substitute in place of B. That is 12 TF into TF as it is. I got TF 39.3. Once I get 39.33, I'll round it off to 40 mm. Now B can be calculated. Width of the plate is 12 TF. B is equal to 12 TF. So 12 into 40, 480. So the step number, this one is over. Okay, step number 3 is over. Now in here what I have done, observe here, step number 3 is over means what I have done, I know the dimensions of flanges like this. I know the dimension of, at this stage, I know the dimension of, so initially I calculated these dimensions, then I calculated the dimensions of flanges. So this is, you just observe here, this one is 480. This is 480, you can see. This is 40 mm. This is 1000. You can see this one. This is 16 mm. Like this, the dimensions are finalized. Now we have to check. Actually, the design is over except welding and stiff bearing check. Stiff bearing, I told to B1 calculation. Except that the design is over, but the problem is whether these are strong enough. We have to check using the standard procedure given in the code book. I have to check it now. Now check the for the moment capacity of the girder. Now actually already we know how much moment it has to resist. That is WL square by 8. Whether this section is going to resist that much of moment or not, we have to find out moment of resistance. Clause 8.2.1.2 is step number 4 is check for the moment capacity of the girder. Now observe this. If you open this page, a clause and all, this formula is there. ZE, you can see again strength of material it is section modulus into bending stress. So here elastic modulus into bending stress I will be taking. MD is equal to ZE Fy by gamma M naught. Now in order to find ZE, elastic section modulus, I should find out IZ by Y. IZ by Y should be calculated. That is ratio between, what is section modulus? Ratio between moment of inertia and Y value. Y is nothing but distance between centroid and the extreme fiber. Observe here how I have calculated. This is again a first year problem. It is reduced to first year mechanics problem. Now observe here. This is 480. This is 40,000. This is 16, 480. There are three rectangles. For three rectangles, you should be able to find out IZ value. IZ means IX. See, whatever you studied IX in all the previous years, in steel structures, the same thing is called as IZ. Don't get confused. IZ is nothing but your IX. Only the notation they have changed it. IZ they call it in steel structures. Now it is IZ is equal to, observe here, this rectangle, vertical, that is web, moment of inertia of the web plus moment of inertia of the flanges. Now observe this, moment of inertia of the web and just observe this part. This is moment of inertia of the flanges. Observe this. Okay. IZ of flange, two flanges, because I'm not going to consider, one more important thing I forgot here. I'm not going to consider moment of inertia of this. Do you know why? I'm going to count only the moment of inertia of this part, it's flanges. You can say flanges and this part. In IZ calculation, you observe this. This web is not considered, which is very important. Only these two you have to, and about this line, about the centroidal line. It means you can see 2 here. This is 2. 2 because 2 flanges are there. So MI of 1 flange it is here. Web is not there. Now 480 into 12 by cube by say BD cube by 12. B is 480 into 12 cube. I think it should be 40 cube actually. This should be 40 cube, not 12. Okay. Then AH square, observe this. A into H square. Are you getting this point? This is 40 cube it is. Into A, the parallel axis theorem it is. IG plus AH square. IG plus AH square. B D cube by 12 plus A into H square. A is 480 into 40. 480 into 40. Area of the flange into H square. What is this 520? 520 is the distance between centroid and midpoint of this flange. See this 520. Centroid and centroid of the entire section and centroid of the flange. 520. So this is 500 up to this 500. Go inside by 20 mm because total is 40. So 520 square. Finally, you end up with this value here. So Y max is how much? Y max means centroid to the last fiber, topmost fiber. It is 500 plus 40, which is 540. This is Y max. See this. Y max is here. Is it clear this one? Y max. Why I should Y max? Because I need IZ by Y max as ZE. Now what I have done here? IZ, that is ZE is equal to I by Y. I divided by Y. So 2 times because 2 flanges are there. 2 into 5.10 divided by 540. I got ZE as 19.2 into 10 raised to 6 mm raised to 3. See this. 19.2 into 10 raised to 6 mm raised to 3 Z value. Now I have to substitute here in this formula. All values are known to us. What is important here is don't consider while calculating IZ, don't consider the contribution of web. You have to only find out IG plus AH square into 2 because this is the centered line. At some distance rectangle is present, that is why I am applying parallel axis theorem. In this way MD is equal to ZE Fy by gamma naught. So only calculation was ZE calculation, which is done like this. After this, let us see this 19.2 ZE into Fy by 1.1 4372. I got the moment of resistance of flanges. Moment of resistance of flanges as this much. Is it safe or unsafe? I have to check factored bending moment. Factored bending moment WL square by 8 is here. So this value is less than the resisting capacity of the flanges. So while the flanges can resist 4372, whereas actual factored bending moment that is acting is 4233. What I can say, moment of resistance is higher than the bending moment. The dimensions are safe. Section is safe now. Whatever dimensions I assumed, if at all MD was less than this factored bending moment, what I should do? I have to increase ZE value, which is a geometrical property. If at all, in case MD was less than factored bending moment, I have to increase the dimensions of flange so that I can increase ZE value. Automatically this value becomes more. Here such situation is not there. It is okay in this problem. Now clause 8.4, check for the shear resistance of the web. Observe here, only web is going to resist the shear. Just 1 second. Okay. But check for shear resistance of the clause 8.4. VD is equal to VN by gamma naught. This formula you refer. Here AV is equal to, see this is the shear resistance. Now Try to understand this one. Shear resistance formula is this. This must be compared with WL by 2, maximum shear force. So this should be higher than that. Now observe, here AV is equal to area of the web. AV FYW into gamma M naught by square root of 3. Okay, it is actually how it is done is it is area into stress into area. These two have come extra. Gamma M naught because of the design partial safety factor. Root 3, why it has come, you observe here. I'll try to tell you how this is developed, how the equations are developed. Actually, this much is a stress they have considered. Usually, see, load is equal to stress into area, but since it is a design subject, I have to divide the stress by partial safety factor. But since it is shear force, I cannot use directly 415 or 250 here. Fy means 250 because shear strength of steel will not be 250. It is tensile or compressive strength 250. Shear will be less. That is why Fy by root 3 is one term taken. To this value, I am dividing it by gamma m. This is the design stress, design shear stress is FYW by root 3. Some constant after some experimental investigations, they say that the relationship between shear strength of the steel and tensile strength is FYW by root 3. So this divided by gamma m. Finally, it is nothing but area into stress only. Now, AV is area of the web. Again, when you calculate area of the web, no question of considering any flanges here. Flanges do not take part in resisting the shear. So VD is equal to, is substitute in this formula here. You are going to get a number 2099. So this is more than WL by 2. See this 705. WL by 2. Factored shear force is 705. Whereas it can resist, the web can resist a shear force of 2099. Actual shear force that is the web is subjected to is 705. It means this is also safe in resisting shear. Check for end bearing. We are about to end this. This is important. It is done in a steel, but you might have forgotten. How do you say that how much it should go inside of the support? I started with B1 as 100. See this. B1 as 100 I have taken. Then I used this formula. This formula is given in the code book. Just check the page numbers. Later I'll give you, no problem, but try to check. When you read these notes, all formula are there in the code book. You don't have to remember anything. You should know the procedure. That's all. That is why still it is very easy to score actually. Because all formula you are not remembering anything. You know the procedure. That's all. You understand the proper procedure. Now FW. Let us say this is somewhere in the code book. Don't worry about that. Now, when you calculate FW should be more than shear force. You try to understand that this much. You calculate this value. If this is more than shear force, it means the bearing B1 is sufficient. Whatever B1 assume, it is enough. If FW is less than VU, then I have to further increase this B1. 100 may not be sufficient. I should go by 150 something like that. I told you practically the entire thing they take. Even if it is a waste of this one, it is uneconomical, but they don't want to bother about another 100 mm. Directly they put it like this. But here, as a designer, you should understand exactly what should be the procedure. Because you cannot you cannot talk like a layman in the site. You should say that I know that this D1 is enough, but still some practical problems I am providing completely. Otherwise, 100 was sufficient. Now observe here. Should I continue or stop it here? 1054. This much is left here. This is important. Already in the beam design, you might have studied it. Here, check for end bearing when I say step number 6. What I am trying to do here, you observe. My job is to simply here, what I'll be doing here is simply this value. See this. Simply I'm going to check this and this. These two I'm going to check. That's all. If FW is higher, I will say this much of bearing is enough. Bearing strength is okay. bearing strength is adequate. Finally, what I got here, this is adequate as it is more than VU, which is 7.5. FW is more than VU. Now worry about how to calculate FW. FW has to be more than VU. Try to understand this. Then start worrying about how I should get FW. FW is B1 plus N2 into TW. See, this is one area. It is simply one area into stress divided by gamma naught. Stress into area. Gamma naught is because of design, partial safety factor. What I'm trying to say here is, just observe this. Ultimately, the formula is strength of material only. This is area. This is stress. Stress into area is force. So B1 plus N2 into TW. Now observe here. B1 plus N2. B1 is assumed as 100. B1 is, to start with, you assume it as 100. Assuming stiff bearing, B1 is 100. Start with 100 mm. Check it. If it is not sufficient, you have to change it. So let us start with simple number 100 mm B1. So B1 is 100. N2 becomes 100. Why? See this load dispersion. How the load line is getting inside here. So it is 1 is to 2.5. I am assuming the slope as 1 is to 2.5. It means to get N2, I should multiply this height, thickness with thickness is 40 mm. Observe here. Once again, I'll repeat. This height is 40. It means this is 40. And this one is N2. In this triangle, this is N2, this is 40. And the slope is 1 is to 2.5. So N2, to get N2, I should multiply 2.5 with this. 2.5 with 40. Because ratio is 1 is to 2.5. So N2 is equal to 2.5 into the thickness, this altitude of the triangle, this altitude into the ratio. So 2.5 into 40, which is 100 again. So this is B1 is 100, N2 is 100, TW is the thickness of the web thickness, 16 mm. Substitute on 250 by gamma m naught is 1.1. You will get a value 727, something like that, which is more than VU. I can say this much bearing is enough. Means it is bearing strength is okay. Bearing strength is okay means what? In simple words, when I say bearing strength is okay means whatever load is there, whatever load is coming from the girder, reaction from the girder will be safely transmitted to the supporting system. It may be one more column or a wall or a pier or abutment, whatever, anything, any structure is there here, this structure. When I say bearing strength, it is safe means the reaction from the girder, plate girder is safely transferred to the column or any other supporting system. It is safe in that. Safely it will transfer now. If at all you try to provide, let us say only 10 mm, B1 is 10 mm. What will happen is it will collapse because the entire reaction, entire load, 50% of the load will be transferred to this support, 50% to the other end. So 50% of the total load will not be safely transferred to the supporting system if you provide just 10 mm or 20 mm bearing here. It means you try to support this girder only for a length of 20 mm or 40 mm. What will happen? It will collapse. That is why we need minimum some distance here so that the entire load is transferred to the support system. That is why this is entire thing is done. Bearing strength and all is calculated just for that reason. So this is the end of your series. Design is actually over. Basic design is basic. I have to design the weld connection here. Welds. I think weld is somewhere it is scrambled. These pages are scrambled here. After this check for end bearing, see this. I have to go with the design, weld design. I think I have not scanned it. Purposely I have not scanned. I think I wanted to finish only this much. In the next classes, I will continue with how this you can say how these three components are interconnected by welding. That is how you connect a web with flange plates using welds on either side. On either side, how it is done, that I will explain in the next classes. So I'll stop it. Any questions here?
No, sir.
Now I'll see. I'll send this. I will post the notes here. Same notes I will be posting. So now, if you see any video of design, you may follow. That's why I told you not to watch any videos, only except those two. Whatever I have posted. Otherwise, there will be confusion because I'm trying to make it simple for the first problem. Remaining two problems along with stiffeners, I will do. End stiffeners and intermediate stiffeners. Usually, if you visit any railway bridge site, wherever plate girders are designed, there will be web stiffeners, there will be end stiffeners, also called as bearing stiffeners. That will be next example. After welding is done, after welding in this problem is done, I will go to one more example. If there is any question, you can ask. Any doubts are there, you ask. Otherwise, tomorrow also you can ask. Go through the notes. There is any questions are there, tomorrow also we can discuss, no problem. Santosh Angadi is having any doubt? If there is any doubt, you ask.
No, sir.
Okay. You go through these notes again, go through those two video clips, then solve this problem. After that also, if there is any confusion here, you can ask me, no problem. So I think all of you have typed your USN, no? All of you?
Yes, sir.
Okay.